Often, an electrical circuit is wired partially in series and partially in parallel. The key to determining the current, voltage, and power in such a case is to deal with the circuit in parts, with the resistances in each part being either in series or in parallel with each other. You can then often reduce a complex configuration of resistors to a simpler circuit, or even to one resistor that is equivalent to the entire original configuration. Consider the following circuit. Connected to the battery is a configuration of resistors that are neither all in parallel nor all in series. We would like to simplify the circuit so that one effective resistor replaces the entire resistor combination. The idea is to identify resistors that are wired all in parallel or all in series, and piece by piece, use the rules for finding the equivalent resistances in each case to simplify the circuit. First, we can determine which resistors are wired in series by identifying those having the same current running through them. Following the current I1 out of the positive terminal of the battery, we see that it splits into I2 and I3 at junction A. We know that the current into the battery must equal the current out of the battery, so that the entire section of the circuit that is highlighted in red carries the same current. A section of a circuit that carries the same current is called a branch. The blue branch carries the current I2, and the green branch carries the current I3. Note that I2 and I3 recombine at junction B to form I1. The two resistors in the green branch have the same current flowing through them and are therefore in series. If we now give the resistors labels, we can find the equivalent series resistance of R3 and R4, which is R34 equals R3 plus R4, and we can redraw the circuit like this. There are no other series simplifications that we can make at this point. Next, any resistors that have the same voltage across them are wired in parallel. Any continuous wires, no matter what their shape, are held at the same voltage. We can therefore highlight the regions of constant voltage in the circuit. Out of the battery, the first span of wire up to the resistor, illuminated in red, is all at the same voltage. Next, the section in green is all at the same voltage, but at a different value than the red segment. Finally, the blue part is all at the same voltage. Looking at the battery, we can see that the voltage difference between the red and the blue parts is the battery voltage. More importantly, the two resistors R2 and R34 have the same voltage across them, green on one side, blue on the other. Since they have the same voltage across them, they are wired in parallel, and we can use our rule for adding resistors in parallel to get an equivalent resistance, which we'll call Rp. We have 1 over Rp equals 1 over R2 plus 1 over R34. Or, solving for Rp, we have Rp equals R2 times R34 divided by R2 plus R34. The circuit now reduces to this. Finally, since there are now no junctions for the current to split, the current must be the same everywhere, and the remaining two resistors are wired in series. Using the rule for adding resistors in series, we have for the total equivalent resistance of the circuit, Re equals R1 plus Rp. But we know what Rp is, so we plug it in to get Re equals R1 plus R2 times R34 divided by R2 plus R34. We also know what R34 is, so we plug it in to get Re equals R1 plus R2 times R3 plus R34 divided by R2 plus R3 plus R4, which is the equivalent resistance of the original circuit. So we have now reduced the resistors in the original circuit that were wired in both series and parallel to a single effective resistor. In summary, simplify circuits that contain both parallel and series connections piece by piece by simplifying series and parallel components using the usual rules. Resistors connected in series have the same current running through them, and finally, resistors connected in parallel have the same voltage across them.